Okay, back at it here in section 1 of chapter 3. You may have noticed if you watched the last video that I didn't do the very last example or two or go over finding the inverse of a one-to-one function. There was a glitch with the camera. I had actually started it but didn't quite record it all, so I went ahead and just going to pick up from there. To find the inverse function of a one-to-one function, and remember only one-to-one functions have inverse functions, my suggestion is to follow these 3 steps. Change f of x or h of x or g of x or whatever the name is to y. Interchange the x and y variables. Make all the x's, y's, all the yx. Then solve for y and replace it, of course, with f inverse of x. This is the notation I finished with the little -1 there. That does not mean to the -1 power. That means f of -1. If you wanted to write the whole thing to the -1 power, and I don't know why you would write f of x like this to the -1 power. But when it's right next to the name of the function, it's the inverse function. So we're going to try that with a couple 3, 4 examples here. This one should be circled in red to go along with the other 2 there, because all 3 of these are examples of problems on the review. We'll start off with this one, which is actually out of the textbook. I'm going to replace f of x with y. I'm going to write y equals 4x plus 3. And then I'm going to solve for, or I'm going to interchange the variables x and y. And then I'm going to solve for y. Solve for y. So I'm going to subtract 3 from both sides. And I'm going to get x minus 3 is equal to 4y. I'm going to divide both sides by 4. I'll just bring it right up here. And I'll put the right side on the left side. So I'll divide this by 4. And I'll divide x minus 3 by 4. And I have y is equal to x minus 3 all over 4. Well, that's my inverse. And so I'm going to write it with the inverse notation. F inverse of x is equal to x minus 3 all over 4. Now you say, well, how would I know if I made a mistake? Is there a way to check? Absolutely. Take this function here and take this function here, and as I showed in the previous example, compose them in both orders and see if you get the identity. It's a little bit of work, but it's a good way to make sure that you have the correct answer. Down here, I'm going to replace f of x with y. Same steps as far as what I'm doing here, same overall steps. I'm going to interchange the variables. I'm going to subtract 7 from both sides. I have x minus 7 is equal to 5y to the third. I'm going to divide both sides by 5. I'll bring it up here. I'm going to interchange the sides. I'm going to write y to the third is equal to x minus 7 all over 5. I'm going to take the cube root of both sides. Now, unlike a square root or any other even indexed root, you don't pick up the plus or minus, because you can take the odd indexed root of a negative number. And I end up with y is equal to the cube root of x minus 7 all over 5. Now, if this was a multiple choice problem on a test, and I look for this answer for my inverse, I might not find it. By the way, f inverse of x is equal to the cube root of x minus 7 all over 5. What they might do is they might rewrite this so that you don't have the fraction under the radical sign, because that is what we usually consider a simplified radical expression. You would have to do a little bit of extra work here to this guy. If this is not one of the multiple choices here, then what I would do is go ahead and go the extra mile here, rewrite this guy right here, rewrite him as the cube root of x minus 7 all over the cube root of 5. Multiply top and bottom by something to rationalize the denominator. Now normally with a square root we multiply top and bottom by exactly the same denominator. But in this case it's a cube root, and if I multiply top and bottom by the cube root of 5, in the denominator I get the cube root of 25, and that's not a perfect cube. So what I'm going to do is take the cube root top and bottom of 25, because if I do this, then in my denominator I get the cube root of 125, which is a perfect cube. So you can take the cube root of it. Over here I would go ahead and rewrite this as a single cube root. I would probably put the 25 first and then the x minus 7. So this turns out to be equal to 5. In fact, let's write it like this. This would be the cube root of 25 times the quantity x minus 7. I could distribute all over 5. You can see why I wanted to stop there, because of all the extra work. You have to be very careful here, but in simplest radical form, remember, no fractions underneath the square root, cube root, fourth root under the radical sign. And there we go. Now these next two examples are very similar, and if they weren't both on the review, I probably wouldn't go through both of these because they're so similar, because they're both rational expressions. They both have the variable in the numerator and the denominator. You're going to see similar steps here. All right, I'm going to go ahead and do this one first. Y is equal to x minus 10 over x minus 7. I'm going to interchange the variables. See how the two x's became y's, the y became x? And then I'm going to solve for y. Now I have the y written twice in the numerator and the denominator both. Not what I'm looking for. So what I'm going to do is try to get rid of the rational expression on the right side. I'll put x over 1 and I'll cross multiply. I have x times y minus 7, 1 times y minus 10. I have xy minus 7x is equal to y minus 10. Now, it doesn't look a lot better because the y is on both sides and I'm solving for y. It means I have to get all the terms with y isolated on one side so I can factor. Well, to do that here, I have to get rid of the minus 7x. If I'm going to get everything on the left side, I'll add 7x to both sides, and I'll get rid of the y on the right by subtracting y. And I'll do it in the same step because I'm a little lazy. So I'm going to add 7x, and I'm going to subtract y, and I'm going to do that to both sides. Add 7x, and I'm going to subtract y. These cancel, and on the right side, these cancel. I end up with xy minus y is equal, xy minus y is equal to 10, negative 10, plus 7x, or 7x minus 10. That looks a little cooler. Factor out the y. You see how now the x is only written, or the y is only written one time? Divide both sides by x minus 1. So bring it up here, I get y is equal to 7x minus 10 all over x minus 1, or f inverse of x is equal to 7x minus 10 all over x minus 1, and I will make the statement that x cannot equal 1 because you can't have 0 in the denominator, and here is my inverse function. You're going to see some similar steps here as I do this next example. Right, this is y equals negative 8x minus 2 all over 4x plus 9. I'm going to interchange the variables. I'm going to write x is equal to negative 8y minus 2 all over 4y plus 9. Put it over 1 here, just like I did with the other example. I'm going to get x times the quantity 4y plus 9 is equal to 1 times negative 8y minus 2, which of course is negative 8y minus 2. I'm going to distribute. I have 4xy plus 9x is equal to negative 8y minus 2. So again, it's up to me to get the variable on one side, the variable y all by itself on one side. So that means these terms here have to be on the same side isolated. So to do this, I'll leave this guy here. I like the positive. And I'm going to add an 8y to both sides. And I've got to get rid of the plus 9x by subtracting 9x from both sides. Do it all in one step again. Hopefully I'm not messing you up by trying to combine steps here. And add 8y, and I do that to both sides. So I'm subtracting 9x, and I'm adding 8y. So what that does is these cancel, and over here, these cancel. So I have 4xy plus 8y is equal to negative 2 minus 9x. I'll probably write that the other way around. I'm going to factor out not the 4y, I know that's the GCF, just the y. That's what I want. And I'll write this as negative 9x minus 2 because I think it looks better that way. I like descending order. I'm going to divide both sides by 4x plus 8. And I'll bring it up here. I have y is equal to negative 9x minus 2 all over 4x plus 8. So f inverse, replacing the y with f inverse, is negative 9x minus 2 all over 4x plus 8. And in this case, 4x plus 8 can't be 0. So if I set it equal to 0 and solve, I'll see I will get negative 2. So x cannot equal negative 2. And there she is. Now remember, only one-to-one functions have inverse functions, and these were given to be as one-to-one functions. But the best way to check would be to compose, but you can see you'd be at it for a while composing those guys. Be very careful. So many steps, negative signs, be very, very careful. Now, what if you have a function that's not one-to-one? Okay, it's still a function, it just doesn't happen to be one-to-one. As you can see in this example here, f of x equals x squared, domain all real numbers, this is not one-to-one. It fails the horizontal line test. What to do then? Well, one alternative, if you really need that inverse, is to limit the domain or restrict the domain. Now, if you can kind of see the symmetry that I have here, if I only had half of this, either this one was gone or this one was gone. Let's say for convenience sake this part was gone. And I really only had this, here we'll use the red pen here, as this is as my part of the graph here. Okay. That means I've restricted the domain. I've now made the domain of this from 0 to infinity. And by doing that, I have, and this is gone, I have a one-to-one function. So I can find its inverse. So I'll set y equal to x squared. I'll interchange the variables. I'll take, in this case, the square root of both sides. Flip-flop the sides. Now here is where we would get the absolute value of y. But remember, I've got a stipulation here that my domain is only the positive numbers, so I don't have to worry about absolute value. I know it's going to be positive. And this is my inverse function. F inverse of x is equal to the square root of x. And again here, x would be greater than or equal to 0 here. Because x is greater than or equal to 0 is not only the domain of this, it's also the range. So the domain of the inverse is equal to the range of the original. Now remember, I just said that this is also equal to the range. So that becomes, because that's what happens. You're interchanging the variables x and y, so you're making the domain of one function into the range of the second and vice versa. And so that's why I would have to restrict the domain here, because it wasn't one-to-one to get this. Now, this function over here is one-to-one. But if I want to find the equation of the inverse, like I was doing here with the domain, I have to be very, very careful here. The domain of g, of this guy, would be from -2 to infinity. Its range of g, if you were to graph this, would look something like this. Its range would be from 0 to infinity. Okay, keep that in mind. Its range, positive. Its domain, well, mostly positive. Now, I write y equals the square root of x plus 2. I interchange the variables. I square both sides to get rid of the radical here. I'm going to write y plus 2 is equal to x squared, and then I'm going to subtract 2 from both sides. But if you remember, this is a parabola. It's just been translated down 2 units from its parent graph. It would look something like this. And this is clearly not one-to-one. Well, somebody's at the door. All right, so what I'm going to do here is I'm going to restrict the domain. Just set it down. You've got to be. It has to be on TV. Okay. Thanks so very much. Yeah, thank you. So what I'm going to do is I'm going to restrict the domain here. The domain of this inverse function, which I'm going to call g inverse of x, is going to be equal to the range of the original function, which would be from 0 to infinity. Now for that to happen, if I'm plugging these values into here, I'm going to get this part of the curve. Okay? It's because of that restriction. So this would be the inverse function of this. So you have to identify what's going on with your domains and your ranges before you can really properly make sure that you are finding a proper inverse function.